Okay, the second part of Chapter 11, where we apply chi-squared to a couple different hypotheses tests. The two tests have different names, but are going to feel, when we execute them, pretty much the same. The way the data is collected or organized is slightly different. So let's look at the data we have here in front of us. Has modern technology changed the distribution of birthdays? So with more babies being delivered by planned C-section, Ms. McDonald's statistics class hypothesized that the day of the week distribution would be different for people born after 1993 compared to people born before 1980. So what they have here almost feels like a goodness of fit. If all we had was one list, this would be a goodness of fit situation. Like if we saw, like, in the group that they had before 1980, 12 babies were born on a Sunday, 12 on a Monday, and so forth, all out of 77. Then they have a group after 1993 where only 9 are born on a Sunday, 11 on a Monday, and so on, but a total of 73 in that situation. So we have two different totals, two different samples. So a goodness of fit situation would be just one of these lists, and we would compare it to, if there's 7 days out of the week, a uniform distribution like 11, 11 every day. 77 divided by 7 would be 11 each. But here we have two lists, so it's a little bit, definitely a different kind of a test that we're going to want to do. But the first thing we want to be able to think about here is a conditional distribution, all right, in proportions. That'll help us to see, do we really see any differences? And then also an appropriate graph. So I'll show you what those two things look like. I'm not going to have us do those by hand. That would be something that we could use technology for, but I want to look at what that would look like. And then, of course, we want to be able to write a few sentences describing what we see in those two situations. So let's look at what that would mean. Basically, the conditional distribution just simply means turn these into percentages. So instead of that being 12, it'll be 12 divided by 77. 12 divided by 77, 14 divided by 77. These numbers here would be divided by 73. These will be more meaningful if we can see percentages. If we can see that there's comparatively a higher percentage born on one particular day, and here we go, we can see on Thursday certainly looks like there might be a big percentage difference between those two, and the student's hypothesis would be because people are scheduling C-sections on Thursdays. So the marginal distribution would look like this, and we can see when we get to Thursday, rather than just using our eye test, we can see we have 9% of babies were born on Thursdays before 1980, but in the group that they had that came after 1993, 23% were born on that day. That seems, for appearance sakes, to be pretty significant. And after 1993, notice there's only 8% born on a Saturday. Nobody's going to schedule C-sections on Saturdays. The doctors are all golfing that day. But before 1980, 14% were born on Saturdays just by random chance. So maybe we can add a little bit more meaning with a graph. We can see for the most part, both of these distributions seem kind of uniform until we get to this Thursday. And I do recall that my son was born on a Thursday, and it was a scheduled C-section. And he was for sure born after 1993. And then a couple sentences. There were a higher proportion of older people born on Tuesday, Saturday, and Sunday, and a much higher proportion of younger people born on Thursday. That's what we tend to see there. We just want to write a couple of sentences describing what we see in that. Now, the chi-squared test that we're going to do, we call this the test for homogeneity. All right, homogeneity means that they would come from the same distribution, which is a way of saying that this distribution of blue bars is not significantly different from the distribution of red bars. Okay, that overall they come from the group of 77 that we got and organized in the group of 73 that we got. They come from the same distribution overall. That's how we articulate this type of a test. So the first thing I want to think about when I'm thinking about any kind of chi-squared statistic is this situation where we have observed counts minus expected counts, and we square that and take the expected. I forgot my summation notation there. But if you remember, we're adding all these up. That's how we come across our chi-squared, so that if the observed and the expected differ by a lot, we get a big chi-squared value. So this test works fundamentally the same as the goodness of fit in terms of how we evaluate chi-squared. We look for a really big chi-squared number. If it's really big, it's always right-tailed. But it's organized a little differently. We're always going to have this two-way table. Okay, and I want to think about this concept of expected counts. Okay, if these two variables come from the same distribution, then how many values would we expect to land in this cell right here? In other words, how many out of the total of 150 people that we have in the sample, if these distributions are if there's no interaction between the year before 1980 and after 1993, if that doesn't affect the distribution, then how many values would we expect to land in there? Just think of basic probability. What's the probability that a number would fall in that cell? It needs to be someone who's born before 1980. So the probability someone's born before 1980 is 77 out of 150, right? There's 77 out of 150 born before there. And they have to be born on a Sunday. How many people were born on a Sunday? 21 out of 150. But this would just give us a decimal, right? And that wouldn't make any sense. We're trying to suggest how many people would we expect to live in there. So we'd have to take this decimal, this probability that a number falls in there, and multiply it by 150. So what happens here is we get 77 times 21 divided by 150. And you'll see that your textbook authors explain that an expected count for a cell is the row total times the column total divided by the overall total. And that's exactly what we just did. Here's my column total, here's my row total, and I divide. So that's where that comes from. I wanted to show that to you one time. But what I want to suggest here is, and I said this with the goodness of fit, when you're doing a chi-squared setup, just run the test first. In other words, get your data organized in your calculator first. Run the test, and you'll see why in a second, because that would be a lot of expected counts to have to go and get. There'd be a total of 14 of them. So that being said, if I want to put this on the calculator, we're not actually going to organize this in lists. What you want to do with this is organize it into a spreadsheet or in a matrix in your calculator. Okay, so if you have the 8384, you're going to use the matrix. In the Nspire version, usually you can put this in a spreadsheet, but you also have the matrix feature as well. So I'm going to run it through the matrix here. And if you did matrices in Algebra 2, maybe you came across this. We're going to hit second and the X inverse key for matrices. And the first thing I need to do, just like I would for a list, is edit the matrix. So this matrix, it's always rows by column. So if you remember here, what did we have? We had 7 rows for the 7 days out of the week, and we had 2 columns. So this will allow me to translate what I have in this list into my calculator, so the calculator can figure out my expected counts and also run the chi-squared test for me. So you can see I take just the counts, okay? No row totals, no column totals, just my counts. We're going to quit, second quit. And now when I go to stat and test, you'll notice that I only have one other chi-squared test. We have our goodness of fit. This is not a goodness of fit. So like I said before, these tests are much more similar than they are different. Their name is different, and the way the data would be collected is different, and I'll try to focus in on that in this video as well. So I'm going to press enter for chi-squared, and notice all it asks for is a observed matrix. Now, I didn't put anything in my matrix B, okay, but we're going to go ahead and calculate that, and the calculator will do it for me. Notice it gets my chi-squared and my p-value. Now, if I hit second and matrix, and we come down to B, look, magically, we have a new matrix there, and it has calculated our expected counts, okay? Second matrix, go to edit, and I have to press the number 2 here so I can get into that. So where did that 10.78 come from, right? Do you remember we did 21 times 77 divided by 150? Okay, 10.78. And there's our 10.78. So the calculator will do your expected counts for you. And remember, what do we need in this situation? We need all of our expected counts to be greater than or equal to 5, and that condition is satisfied. So if you're doing an actual hypothesis test here for chi-squared, remember, you need an SRS. You need to check that your expected counts are greater than or equal to 5. And it's not enough just to say that they're greater than or equal to 5. You would have to list them. Okay, so I can take those expected counts and list them. And yes, I cheated and copied that. Let's see, do it again, Control V. Oops, now it's in there twice. Don't really need 2 of them, just 1. But these are my expected counts, and I would list them. Okay, so it's row total times column total divided by the total just one time, 150. So the table below shows our observed and our expected counts. We have them all. How do we calculate the chi-squared statistic? Show your work. Well, we would let the calculator do this all the time, but I'm going to just write down that it's the observed minus the expected squared divided by the expected, and it's a summation. So I have to add a bunch of stuff up. So I'd have to take 12 minus 10.78 divided by 10.78 plus, we just keep going through here systematically, 9 minus 10.22 squared divided by 10.22, right? And keep adding them up all the way till I get to the very last observed and expected, 6 minus 8.25 squared divided by 8.25, okay? And what was that value? It was 6.549. Okay, and remember our calculator conveniently gives us the p-value, and we have a degrees of freedom of 6, right? So where did our degrees freedom come from? For this other chi-squared test, remember it was before, it was just the number of categories minus 1. Well, we have a number of categories kind of double here. So what we do for our degrees freedom now is rows minus 1, since it's a two-way situation, times columns minus 1. So we had 7 rows here. So 7 minus 1 is 6. So this would have been 6 times, and we had 2 columns. 2 minus 1 is 1. And that's where our 6 degrees of freedom comes from. So that is something you're going to have to commit to memory for the new chi-squared test. The degrees of freedom is rows minus 1 times columns minus 1. In the chi-square goodness of fit situation, it's just number of categories minus 1. So notice how this null and alternate hypothesis reads, because I want to differentiate between what our chi-squared test of association or independence would read. But we had 2 different groups that we took, and we arranged them in distributions. So there's no difference in the distributions. This is your chi-squared test of homogeneity to see that they come from the same distribution, or that their alternate hypothesis that there is a difference. Okay, to verify the conditions that for this test was satisfied. So the first thing that we needed was that we had a simple random sample. And here we see right in the narrative, they selected a random sample of people. Okay, so that's going to be satisfied. Okay, SRS is stated. We already listed our expected counts. I don't want to put a P here. But both samples are less than, so we have 1, 2, and 3. And this third condition, our 10%, we actually don't do that for the other chi-squared test because we're testing to see if they're independent of each other. But in this case, we're saying that both samples are less than 1/10 of the populations. When we do the test for a chi-squared test of association or independence, we don't list that because we're not looking to see if they're independent as a condition. We're trying to test for it. To find the p-value, we have our p-value right there, 0.364. But if we used our table for that, let's see where that comes out. So if our chi-squared value is 6.549, our table won't give us an exact value. We have 6 degrees of freedom, but 6.4 would be over here, right? Or 6.549. Doesn't even show up on our table. If this is 7.84, this is where 7.84 lives, and they're telling us that this probability is 0.25, then for sure, if we have over here 6.549, then the area is bigger than 0.25. So all we know from the table is that the p-value from the table is greater than 0.25. That's all we know. But from the calculator, we know more specifically it's 0.36 and so on. Okay, so interpret the p-value from the calculator in context. Okay? The p-value means that, let's just write it down first so that we have that, 0.365. This means that 36.5% of the time. So the p-value, again, still means the same thing that it's meant for several chapters now. It just means that it's the probability we would get a sample like this if the null hypothesis is true. It's not unusual to get a sample like this, these two samples, and compare them if the null hypothesis is true. So that means that we would fail to reject H0. Even though we had that big difference on Thursday, it wasn't enough to be significant, okay? So that means we don't have significant evidence that the distributions are different. Now, if we wanted to just focus in on Thursday and see if there's a significant difference in proportion of births on Thursday after 1993 as compared to before 1980, we would do that separately. But that's not what their question was. There, in general, overall, has a distribution of days of the week that children are born changed because of the advent of more common C-sections, and we don't have significant evidence to believe in that. Okay, before I look at the last example, I want to go to, on our Schoology page, up at the top, choosing the correct inference procedure. This is an exercise I'd like everybody to try on your own and experiment with, but the goodness of fit is pretty recognizable. You'll have like one list of data, but I want to right now just focus in on the difference between the test for independence and test for homogeneity. This is going to be important, so I'm only going to click those two boxes. Is the type of music that people listen to related to the state that they were born in? 10,000 Americans were asked what type of music they listened to and where they were born. So here you have one sample, 10,000 people, and they're going to answer those two questions. You will be able to organize the data into a two-way table, right? Type of music, state born in, and test for an association. But because we didn't take two separate samples, we only took one big giant sample, this is your test for independence. We didn't do one of these in our examples. We didn't come across any. But we look in the narrative to see, did they get two separate samples that were already stratified ahead of time? That would be the test of homogeneity to see, do those samples seem to come from the same kind of distribution? Do Democrats and Republicans have the same phone carrier usages? 554 Democrats, 672 Republicans. You can imagine the two-way table here, Democrat, Republican, and then phone carriers. But we have two separate samples. We have a sample of Democrats and a sample of Republicans. If we took just one giant sample of 1,000 people and said, what's your political party? What's your phone carrier? That's the test of independence. This is the test of homogeneity because I took two separate samples and I want to see, do they seem to come from the same distribution? Is there evidence that they're not the same distribution? Is blood type related to astrological sign? Here's 3,000 people, right, that we sample. And we want to see, is their blood type related to their astrological sign? We actually had the goodness of fit test kind of felt like this with the blood type question, but it was, I think, personalities. But this is one big giant sample. So when it's one big sample, it's a test of independence. Among that sample, do we see an interaction? So it's sort of like finding a correlation where we can't do a scatter plot, right? We have categorical variables, which makes this chi-square test of independence a pretty powerful tool. So we'll look at the last example here, and when it says compare the distribution of color choice for each of these three treatments, that just simply means we're going to look at, 65 on the red survey, 65% of answers were red. On the blue survey, it looks like 75% were blue. And on the control survey, 12% were blue. Okay, so we would just look at those percentage breakdown. And a segmented bar graph might be a decent way to look at that. We can see big difference on the red survey, they favored red. On the blue, they favored blue. But again, this is just our eye test. We're not doing anything statistically sophisticated to see if these differences are just by random chance or if they're significant. So let's try to think about the hypothesis test from start to finish. What would that look like? So our null hypothesis would be that there's no difference in the true distribution of color choice for people who get the red survey, blue survey, or control. They're all the same. Alternate is that there is a difference. Notice in our conditions, we need to take a random sample, but this is an experiment. So we're randomly assigning treatments. So this is different. Therefore, our 10% rule doesn't apply either. We're not thinking about sampling less than 10% of the population because we're really sampling without replacement. We're doing an experiment, giving out this red survey, blue survey, and control survey, and we can imagine that there would be infinitely many surveys to choose from, or respondents to choose from. And then our large counts, remember how we do that. We're going to let the calculator do that for us, but it is row total times column total divided by the total. So if we're wondering where that expected count came from here, it would have been 26 times 20 divided by 60, right? This expected count inside here, where we see an observed count of 5, would be 26 times 20 divided by 60, okay? And we can check those. But remember, our calculator is going to do the heavy lifting for us here. We're going to set this up with our matrices. I'm going to hit second matrix, and I'm going to go over to edit. The old matrices are still there. Press enter. But this time, I only have 2 rows, and I have 3 columns in my matrix. Okay, and I'm going to enter the observed values that we have. So my matrix looks like this. And now, remember, if you just execute the test first, that's probably what I would do even before I write my null and alternate hypothesis. I go ahead and execute my chi-square test, okay, and let the calculator know. Because when you go to check your conditions, you need expected counts. There's no sense in calculating all those expected counts by hand when the calculator is going to do it for you. So we get our chi-squared statistic of 6.65. We get our degrees of freedom. And now, more importantly, I'll be able to go to my matrix, go to edit, and select number 2, and I have all my expected counts. Because part of my condition for inference here is to say the expected counts are all greater than 5, and I want to list them in order to be able to say that. So you can see they're all right there, just like they are here on my solution page. Okay, so our chi-squared statistic is 6.65. We have 2 degrees of freedom, and we get our p-value of 0.0359. Everything that we have right on our home screen here. And so this leaves us with 2 chi-square tests, and with a p-value of 0.0359, our result is going to depend on what our significance level is. So if we're using an alpha of 0.05, we believe that p-value 0.0359 is significantly less than that, and our results would be that we have significant evidence that the way the survey was worded affected the way people responded. That's how that chi-square test works. So you really have 3 total tests for a chi-squared. You have this test of homogeneity here, okay, which we've done. Those are the only examples we've done today. We did not do a test of independence from start to finish, but you can go to that applet that's right here on the Schoology page and test for the difference between them. You can even add goodness of fit to this, okay, as a good exercise, right? You suspect that a casino is using a roulette wheel. That is unfair. You observe the outcome of the wheel 900 times to see if each number is equally likely to occur. So all you would have in this situation is one list, and you would be comparing the number of times those values came up to the claimed distribution that they would all be equally likely. So this is going to be a goodness of fit situation. Okay, that's what we did in 11.1. The 2 that are mostly confused are the independence and homogeneity, because that data is going to be organized into a 2-way table, and it's going to feel very, very similar in terms of its execution. So if you name the test wrong, it's kind of a minor detail. It's more important that you can run the test and also articulate an appropriate null or alternate hypothesis, and then the correct conclusion based on it.